Here are a few examples of the substitution that we've been talking about to do the integral of power of sine times the power of cosine. In the first one here, this is the easiest possible thing. Notice that not only is the power of sine odd, but the power of sine is actually 1. So that means that our first step, which is to separate off one of the odd powers to go with the dx, is then in effect separating the entire sine of x part off. So all of this stuff is going to be the du part of our substitution. And then the only question is, so the substitution would be u equals cosine. And then the du is going to have a sine times dx in it. Notice that everything else here already is in terms of cosine. So I don't have to do any of the extra stuff with this one that I did with the other one. So I can just go ahead and do the substitution problem. U equals cosine x, then du is negative sine x dx. So that negative is something we'll have to take care of. If it's me, I'm going to multiply on both sides by -1 so that I have both of these things to use now for my substitution. And if you look at the pieces that I have, I can take care of everything that's in that integral using one of these two things. So cosine to the fourth will be u to the fourth. Sine x times dx is negative du. And I can put that negative sign out in front. Antiderivative of u to the fourth is 1/5 u to the fifth. And then substituting back in, u is the same as cosine, so I'll have negative 1/5 cosine to the fifth. So that's the easiest possible thing that can happen, that we don't have to use the trig identities at all. We can just separate things out in terms of sine, one sine, and all the rest are already in terms of cosine. And number 2, this gets at what I was talking about the power not mattering. I have square root of cosine here. And of course, square root of cosine just means cosine to the 1/2 power. So I'm going to separate out one of the sines to go with the dx. So first thing I'm doing is identifying that I have an odd power of sine, so I can separate one of those sines to go with the dx, which is what I've done here, and that'll leave me with sine squared here. The reason I want to have an even power left here is because I can change that into an expression involving cosine. So sine squared is 1 minus cosine squared. And I still have the square root of cosine, which I'm going to write as cosine to the 1/2, and then times sine x dx. This is a definite integral, so I'll carry this information around as well. I just have to remember to evaluate a number at the end. The substitution here then is the same as it was before. Here's my du is supposed to be the sine x dx, so that means my u is going to be cosine. And so I really have exactly the same stuff that I have up there in the blue boxes to incorporate here. So I'll have 1 minus u squared times u to the 1/2 times negative du. And so this negative sign can be put here where this just gets reversed. And then I multiply that through. So I have u to the 2 times u to the 1/2 is u to the 5/2 minus 1 times u to the 1/2 is u to the 1/2. Now note I did not, I forgot to change my limits of integration. I typically do that. You don't have to. You can always just get the answer all the way back in terms of x and use 0 and pi. But let me just point out up here that when x is 0, u is 1, and when x is pi over 2, u is 0. So the reason I wanted to point this out is because it does feel a little weird that your integral comes out to go from 1 to 0, which we don't normally see. We normally see the smaller number on the bottom. But this does happen sometime with substitution. It's actually flipping our our interval around with this particular substitution, and there's nothing wrong with that. So if I do the antiderivatives here, I know that I need to add 1 to the power and divide by that new power, and then the same with add to the power, reciprocal of that power, and then this gets evaluated from 0 to 1. And so when I plug 0 in, I'll have 0 minus 0, and when I plug 1 in, I'll have 2/7 minus 2/3. And so eventually this will be 2/3 minus 2/7, which is, what, 8/21 or something? Anyway, so I get a final numerical answer at the end. The last problem here is actually the same problem that you did on the first assignment, where we were talking about just rewriting the integrand. And remember, the idea was that we're using trig identities for cosine 2x, because there are 2 of those. And the one that's useful here is the fact that cosine 2x is 1 minus 2 sine squared x, because that can be solved for sine squared to get 1/2 1 minus cosine 2x. So this fact allows me to just simply change the problem down here. I'll try to keep them both on the page at the same time for a second. So here I can, before I do any calculus at all, I can just rewrite this integrand like that. And there aren't a whole lot of times where that expression seems easier than sine squared, but one of the times that it's easier is integration. Let me get rid of this, get it out of the way. Our integral rules make this fairly straightforward. I have the 1/2 that sits out front. I have x minus, and then I have 1/2 sine 2x. So that's my final answer without having to drag other things into it and without having to do any explicit substitution. I'm just using the double angle formula for cosine that happens to be an expression involving sine squared. So that's the idea. There are some online homework problems for 7.3 and 7.4. The first few are from 7.3. Those are definitely worth going ahead and doing. The third and fourth problem on that homework set are part of the quiz that you'll do for the assessment on this material before we move on to the next part. The reason that homework assignment says 7.3 and 7.4 is that it's really the 7.4 stuff that I want you to see before the semester ends. But what you'll see is that in 7.4, we have a method of approaching an integral that turns an integration that has no trig functions in it at all into one of these integrals that has powers of sines and cosines in it. So there's no point doing that if we haven't at least talked about how you would evaluate the integrals of powers of sines and cosines.